Those are online. Is the school closed today? Those are online. Am I audible? Am I audible? And, those are online. Am I audible?
Yes, sir.
I'm asking, is the school closed today?
Yeah, so today we have study holiday.
That's Laya. What about others? Adarshini,
Sir,
is the school leave today? Is it a holiday?
I took leave today.
You took leave. Okay. Just seeing that most of you are at home. Here, no one has come. Just waiting for others. Can you just give me 2 minutes of time?
Sir,
Yeah.
sir, this is Sri Kriti, sir. We are on the way to the tuition, sir. School left us late.
Okay. I want you all to come. It's an important topic. Others, just give me 5 minutes of time. I'm just waiting for some. Those who are online, you can just go through the last concept that we discussed, that is about the alternating current. I remember teaching you eddy current also. You can go through the AC generator, go through the AC generator and be ready. Once these people come here, I'll start the class. Okay, I need 5 minutes because it's important topic. I'm just holding it before starting. Okay, I'm going to start the seventh chapter today. Yeah, those who are online, am I audible? We have only few here. Shall we get started?
Yes, sir.
Are you able to see my screen? Anyone else joining, or only you both are there? Or yaru illiya school lo? Most of them are on leave. At least had you informed me, I would have cancelled classes, physics classes for you guys. எனக்கு தெரியாது. நான் வந்து I thought only for 11th I am doing it. அவங்களுக்கு தெரியும் எனக்கு. I know the DAV has exam. Daya, are you there?
Yes, sir.
When are your exams in school?
We are having exams now.
So it's currently ongoing.
Yes, sir.
Then I would have cancelled it. It would have been complete. என்ன கிளாஸே வச்சிருக்க மாட்டேன். டிவைஸ் நான் என்ன பண்றது? டிவைஸ்க்கு யூ ஹேவ் டு ஆஸ்க் மீ. எனக்கு அட்லீஸ்ட் முன்னாடி தெரிஞ்சா ஐ கேன் ஆஸ்க். ரேண்டமா வந்த கொஸ்டின்ஸ் டிஃபிகல்ட். அட்லீஸ்ட் யூ ஹேட் டோல்ட் மீ லாஸ்ட் வீக்கே சொல்லியிருந்தா கூட ஐ வுட் ஹேவ் பிளான்ட் இட். I wanted to start this chapter. I told you last week itself I'll be starting this chapter. Why didn't you people tell me? We got a message today morning only that someone else asked for the class, நாளைக்கு class வந்து hold பண்ணலாமா? Physics, I thought I can do it because it's completely DAB batch. பண்ணியிருப்பேன் நானு. You would have studied. Next week also you have, no? It's still 20? 10 days.
Sir, it's till 23, sir.
Okay, almost 10 days. Starting from 14th, 10 days. What should I do now? Shall I start this? You're okay? Tomorrow I'll close off. Another class there. And next week also you don't need, if I'm not wrong. Correct? Next week you don't need classes. So 18th anyways we are closed because of Ganesh Chaturthi. 19th I'll hold it. Is that okay with everyone? Because எனக்கு ஒரு problem என்னன்னா, I want to start off with the test series. You know about the test series, right? We'll be conducting, once the portion is over, we'll be starting off with the tests, continuous test strip, test and paper discussion, so that you will be able to master the papers faster. அது வந்து will be starting in the month of November. If these delays are coming up, it will be difficult for me. Because 25th வந்து I have scheduled a test for you guys. This month 25th, I have scheduled 2 tests. 25th and 27th. Electromagnetic induction and moving charges and magnetism. What should I do now? Should I start this? Or you guys want of any topic that is not clear from the one which is there for your test? Guys, at least open your mouth and speak. I'm asking for you guys only.
So moving charges.
Toroid illa, deleted. Toroid is not. Toroid. Toroid. It's not there, it's deleted. Okay, I can teach that, not a big deal. Velocity selector, you people asked. Okay, that I will teach. Okay, that makes sense. We'll start with that at least. Do you have the 5th chapter for test? Up on the topic varum. Okay, I'll teach that. Maybe that makes sense. Then a quarterly as a சொல்லுவாங்களா அதுவா? How உங்களுக்கு யூட்டியா? ஒரு சில ஸ்கூல்ல பிஏன்றாங்க, ஒரு சில குவார்டர்லின்றாங்க. ஏதோ ஒன்று, பட் It's a cumulative test, right? I'll do that. Just give me a minute. What are the topics? Toroid. You need toroid and velocity selector. That one I'll teach. I think I can complete all the three. Let me see what best I can do. But did you all go through the video of solenoid after I told you from the app? Only if you understand that, you will understand this part. Okay. I'll do one thing. I'll first do velocity selector, and then I'll do the topic that is there in the textbook. That is the relation between theta. Because toroid is a deleted topic. I doubt it is there for the syllabus. I don't know why they taught you. That I'll keep it as the last priority. Okay. You have textbook now? On the topic பேர் எனக்கு சொல்லுங்க. That's calculating the time period. Okay. Shall we get started? Now listen. So now we'll get started with this topic of something called as velocity selector. The name itself is suggesting something that is related to velocity and selection process, right? So the question is, where are we going to apply this concept, right? Now, let's say you have a charged particle and the charged particle is projected into a combined electric and magnetic field. So if you observe, this velocity selector falls under the chapter moving charges and magnetism. There we see, we only discuss about the concept of charged particles moving within a magnetic field. We know that it experiences force according to the Lorentz force concept, right? But the question is, what if there had been a situation where there is electric and magnetic fields mutually perpendicular to each other, and I repeat it, listen to this carefully. What do we have in the concept of velocity selector? You have electric and magnetic fields. And how are those two? They are mutually perpendicular to each other. And the velocity of the particle which is projected into this combined electric and magnetic field is also going to be perpendicular to the other two. So to put it simple, velocity, electric field, and magnetic field, all the three are going to be perpendicular to each other. If this kind of a scenario is supposed to occur, if you want the three vectors, velocity, magnetic field, and electric field to be perpendicular to each other, that is possible only in the three-dimensional space. So what we will do now is we will assign one direction to electric field, we will assign one direction to magnetic field, and we'll assign one direction to the velocity, right? So having said that, if I take the electric field to be in the upward direction, okay, and At this point, I'm putting an into mark and a circle around, where this into mark and a circle is going to represent the direction of magnetic field. So here, electric field is in which direction? In the y direction. Magnetic field is going to be in the negative z direction, right? So y and z are exhausted. So what should be the other direction left out? That is x. So I am going to project this charged particle V along the positive x direction. Okay, makes sense? So when I project it into this, project it along the x direction, now the important question that I need to answer is there a possibility for this charged particle to move undeflected? So what am I trying to achieve? What is the objective of this experiment? I want the charged particle to travel undeflected. So this is the word across which I'm going to think of the whole experiment. So if I wanted to go undeflected, means if I project it along the x direction, right? So if I project the charged particle along the x direction, the particle should have gone, the particle should continue to move along the same x direction. If that should happen, then what should be the condition? Then the force experienced due to the electric field and the force experienced due to the magnetic field should be in such a way that they get nullified. Nullified in the sense, the electric force and the magnetic force on the charged particle due to the individual fields should get cancelled out. If that should happen, let's see how the mathematical expressions are to be written. Okay. So the first question is, I'm going to observe what will happen to the charged particle in the presence of electric field. So we know that when a charged particle is projected perpendicular to the electric field, what is going to happen? It will travel in a parabolic path. So I'm not talking about the combined effect. I'm breaking the system into two parts again. I'm trying to understand what will happen because of electric field. That doesn't mean I'm not going to be concerned about magnetic field. I'll come in the next step. Okay, the first step is what happens due to the electric field. So due to the electric field, what will happen is, since V is perpendicular to E, the first thing to be noted is whenever a charged particle is projected perpendicular to electric field, the particle will travel in a what kind of a path? Parabolic path. So the particle is going to travel in a parabolic path, but that is not a major concern here. This is an extra information. Because in some question, if they ask you what is going to be the path, you should not write circle. Because we have discussed about circle. Circle will come into picture only in the presence of magnetic field. Okay. So it is going to be parabolic path. But the important question I need to answer is what is going to be the force experienced by this? So force exerted on the charged particle, the electrostatic force experienced by the charged particle is going to be equal to the charge multiplied with electric field or the intensity of electric field. Simple. Now, it clearly tells me that due to the presence of electric field, it is going to experience a force in the upward direction. Okay. Now, what did I say? I told you something in the beginning. What is the objective of this whole experiment? I want the charged particle to travel undeflected or undeviated. Meaning, if I project it along the x direction, it should move only along the x direction. It should not go in any other direction. If that should happen, right? If that should happen, tell me what should be the net force experienced by the charged particle? Obviously, it should be 0. We know that the electrostatic force or the electric force on the charged particle is acting in the upward direction. So what should be the direction of magnetic field so that it gets cancelled? If one force is in the upward direction, what should be the force experienced by the charged particle due to the magnetic field for it to get cancelled? You tell me. It should be in the downward direction. So if I want the magnetic force to exist in the downward direction, then I need to do some analysis to this. That is, I'm going to get into the second condition. Second condition is in the presence of magnetic field. What is going to happen? Here, one thing is clear, that the velocity is perpendicular to magnetic field. No doubt in that. Velocity is perpendicular to magnetic field. But the question is, The velocity being along x direction and magnetic field being along the negative z direction, what is going to be the direction of force experienced by it? So it is going to be v vector cross b vector, right? So whenever you are applying, whenever you need to calculate the force on a charged particle, either you can use the right hand rule or you can use the Fleming's left hand rule. Okay, so here I'm using right hand rule because I'm doing the cross product. I know that force experience is equal to q into v vector cross b vector. Here I'm taking the charged particle to be positive. So v vector cross b vector means velocity vector is in the direction of I cap cross, what is the direction of b cap in this case, which I have considered? It is minus k cap. So what is I cross k? I cross k is minus j. I cross k is minus j, but I already have another minus sign. So it will be plus j. So that tells me that the force experienced by the charged particle due to the magnetic field will also be in the upward direction. That gives an indication that the direction of magnetic field I've considered in this case is wrong. So what should be the direction of magnetic field I should consider? Okay, this is a part of the experiment only, understanding in which direction we are supposed to consider the okay. So here, if you observe, the direction of magnetic field is not going to be into the plane, rather it should be out of the plane. When it becomes out of the plane, this minus I cap is going to become, sorry, minus k cap is going to become plus k cap, and I cross k is going to be minus j, which is going to be downward direction. And what is going to be the value of the force? The value of the force is very clear. Fb is equal to, it is going to be QVB sine theta. It is going to be QVB sine theta, where theta is going to be 90 degrees. So it is supposed to be Q into V into B. What did I say in the beginning? The forces are supposed to be in such a way that they will be opposite to each other. But if the force has to be zero, if the net force has to be zero, then what should be the relation between their magnitudes? They should be the same, right? They should be the same. So electrostatic force should be equal to the magnetic force. That implies QE is equal to QVB. Q and Q will get cancelled, which implies V is equal to E divided by B. Meaning, if there is a perpendicular electric and magnetic field system, you need to project the charged particle with velocity V, which is equal to E by B, in the direction perpendicular to both electric and magnetic field, so that it travels undeviated. Is the point clear? So this is all about the concept of velocity select. Clear?
Sir, hello, sir. Sir, sir, can you do torque due to current carrying loop, sir?
I didn't get you.
Sir, torque due to current carrying loop.
Okay, I think it is already there. 1 minute. I'll show you. I've already put it on YouTube itself. I'll share a link with you. You can have a look at it.
Okay, sir.
Guys, I've shared a playlist of the 4th chapter itself, that is moving charges and magnetism, in the chat box now in Zoom. Okay.
Okay, sir. Thank you.
Adala, you go, there are 13 videos. In those 13 videos, right? I'll tell you, I didn't put the lecture number alone. So in the 13 videos, right, you will have something called as negator torque experience by current carrying loop placed in magnetic field. 25 minutes video report. You can go through that. Okay, it is actually the class recording, not the screen recording.
Okay,
You will
sir.
see the demonstrations also, whichever I've shown.
Okay, sir.
Okay.
Thank you, sir.
ஆப்ல இல்ல இது யூடியூப்ல போட்டது. நான் அனுப்புறேன். Send it. ஒண்ணும் இல்ல, you go. I'll wait, I'll do one thing. சேனல்ல இருக்கும், there is a playlist called as moving charges and magnetism. அதுல வந்து I put all the videos. வேற ஏதாவது டாபிக் வேணும் கூட சொல்லுங்க, I'll add it there. இதெல்லாமே கிளாஸ் ரெக்கார்டிங், இப்போ ரெக்கார்ட் ஆகுது இல்ல, இந்த ரெக்கார்டிங்ஸ் எடிட் பண்ணி போட்டுதாங்க. சரியா? அதனால that is why I'm not teaching it again, right? It will take 25 minutes. அதை பார்த்துக்கோ, புரியலன்னா you can definitely approach me. சரியா? So this one also I didn't teach, no, so recording will not be there. This I'll teach and explain, put it there. Shall I proceed? Those are online, shall I proceed? Yeah? ஒரு நிமிஷம் புக் தான். So write down the setting. Is new book either? The new or old book? Okay. So it is in page number 178. For those who want to see, it is in page number 178. Okay. Listen. Yeah. So the next topic that we will discuss is magnetic dipole in a uniform magnetic field. Okay. So here if you observe, right, let's say there is a uniform magnetic field that is existing. So in this uniform magnetic field, there is a magnetic dipole that is placed. There is a magnetic dipole. I'm taking a bar magnet, for instance. Okay. So it is going to have pole strengths of Q and Q. I'm not getting into those details. So the magnetic field's value is B. Right. So first question that I need to answer is, right, when you place a dipole, when you place a magnetic dipole in external magnetic field, what is the first thing that happens? It experiences torque. So the first question I need to understand is, see, I'm going to answer the questions in sequence so that I'll get some answer at the end. Okay. The first question I'm asking myself is, what is going to happen to a magnetic dipole when I place it in a magnetic field? In an external magnetic field, it will experience torque. And what is going to be the value of torque? It is going to be mb sine theta, where m is going to be the magnetic dipole moment, b is the magnetic field, and theta is going to be the angle between them. Right. Now the second question is, if I just rotate this particle, listen to this carefully. If I take this dipole, I rotate it to a very small angle. I'm not rotating it completely. I'm rotating it to a very small angle of d theta and leaving it. What am I doing? I'm rotating it through a small angle, d theta, and leaving it. Now, what do you think will happen to this? The particle will start oscillating. So whenever you disturb the particle from its equilibrium, from its position, and rotate it and leave it, right, it starts oscillating. We will prove that it is going to oscillate by using some mathematical expression. So what am I doing? I rotate the dipole through a small angle, d theta, and leave, what will happen? I told it is going to oscillate, right? But I'm going to prove it using the mathematical equations. For that, I'm going to use the first equation only. What is it? It is the torque which is given to be equal to mb sine theta. Am I right? Now, what is the angle through which we have rotated? I told d theta, right? That d theta can be approximated to theta itself. Okay, I'll tell you what I'm doing. Now, listen to this carefully. If there is a force acting on an object of mass m, what is it? If there is a force of F acting on an object of mass m, it experiences an acceleration given by the expression F divided by m. We know this because it comes from the expression of F is equal to ma, which is basically the Newton's second law, mathematical expression for it. Now, if I replace the force with torque, then torque will produce what kind of an acceleration in an object? It will produce angular acceleration. But the objects, the equivalent of mass in rotation is going to be moment of inertia. So it's going to be I, which is the moment of inertia. Point to be noted here is because I wrote the I like this, don't confuse yourself with current. It is the moment of inertia. Is the point clear? Now, can I take that and substitute it here? Can I write I into alpha is equal to mb into sine theta? Right. So I is I only. This alpha, can I write it as d square theta by d theta square or dt square is equal to mb into what is going to happen? So this torque is due to whom? This torque is due to the external torque that I applied. The external torque that I applied caused a displacement of how much angle in the position? It caused a displacement of very small angle, d theta, right? So instead of d theta, I'm just writing it as theta, where it is going to be a very, very small angle. Or else I'll use some other notation here. Shall I use another notation or you're okay with this? You're okay with this? You're able to understand this? So mb into, can I write it as sine of, okay, I'll write it as sine theta itself. Now see, I'll write this as mb into, whenever the angle through which it is rotated is going to be small, sine can be approximated to the angle itself. Can I write it as theta? Right. So if I rearrange the equation, d square theta divided by dt square is equal to mb divided by I into theta. If you observe this expression, it will look similar to alpha is equal to omega square theta. We know that this equation exists for simple harmonic motion. You remember A is equal to minus omega square x. That is the mathematical expression for any particle in SHM. So A is replaced with alpha, omega square is omega square only. In the place of x, you will write it as theta. Then this is also the case of simple harmonic motion. So what has happened is the external torque that we applied has caused a rotation of d theta or theta in the position of the object so that it started oscillating. Now, all that we need to find is what is going to be the time period with which it will oscillate. So if you observe, alpha came out to be mb divided by I into theta, where this alpha is nothing but d square theta divided by dt square. So if I compare it with the standard expression of simple harmonic motion, alpha is equal to omega square theta. I didn't put the minus sign here because I know it's a restoring torque. So what is going to be the value of omega square? If I compare both the sides, omega square is mb divided by I, which implies omega is equal to square root of mb divided by I. And omega is how much? 2 pi by capital T is equal to square root of mb divided by I. So time period will be equal to how much? 2 pi into square root of I divided by mb. So this is the expression for the time period with which the dipole is going to oscillate in the presence of magnetic field. Am I clear with this? Right? So this is what is given in your textbook. Right? You can make a note of it. Those are online, are you clear? Good. So just make a note of it. புரியுதா? Is it clear? Did they teach this concept? But see, sometimes, very often, very rare is it, the question கேட்கறது. It's very rare. I have not seen much in boards. But all they ask, you can make use of this. Rotation when they see oscillation another. When you say an object is oscillating, what is the important point in you which you consider? You say there is a to and fro motion. So to and fro motion will take place about some position called as mean position. Whereas when you're saying an object is rotating, it will rotate about an axis. So there is a difference in the language itself. So they both cannot be seen. இங்க வந்து டார்க் வந்து என்ன சொல்றேன்னா, I've disturbed it from its equilibrium position. Initially இப்படி இருந்தது, I've disturbed it. If I disturb and leave it, then this will happen. See, let's say there is a U-shaped track like this. Okay, imagine you would have seen it already. There is a U-shaped track. I release a marble from here. What will happen to that marble? It will go down and it will go to the other side, and is it going to stop? No, right? It will start oscillating about that mean position. That U shape is there, no? The vertex of that parabolic path will be the mean position. So it will start oscillating about that mean position. So that is called as oscillation. You cannot call it as rotation. So oscillation again need not happen only along the curved paths. It can happen along a linear path also. Best example is you take a spring and a block suspended, pull the spring from its equilibrium position, leave it. It starts oscillating. So this is a linear oscillation. So when you have linear oscillation, you will use A is equal to minus omega square x. When you have this kind of, what do you say? An oscillation other than the linear path, on a curved path, then you are going to use alpha is equal to minus omega square theta. These two are the very basic expressions of simple harmonic motion. I hope those are online could understand. Those are online, did you understand? Are there any other topics? Toroid, la? And take only 2 minutes. Simple topic. Shall I explain that? Next slide. Okay. Yeah, for the others. So the topic we'll be discussing is toroid. So this is basically a solenoid, which is a linear shaped coil, right? Which is bent in the form of a circle. Then how is it going to be? You have a core. Let's say you have a core, and around this core, there is a winding like this. Okay, there is a winding of this sort, which is actually, if you break it and open it, right, it look like a solenoid only. But when you bend it, it is going to look like a, in this shape, we call it as toroid. Both have the same kind of application. Only thing is space saving activities will come into picture. Okay. So for this toroid, you have an internal radius A and you have the external radius to be B, meaning the radius of the outside portion to be B and the radius of the inner portion to be A. On an average, let's just take it to be R. So the first point to be noted here is, for a toroid and a solenoid, magnetic field outside is 0. So if you take this to be the solenoid, if you take this to be the winding, right? If you consider it to be a long solenoid, what is the meaning of long solenoid? Length is more compared to its thickness, right? If you take a long solenoid, for it, the magnetic field is going to exist only within it. Outside means on the top and at the bottom, the magnetic field is considered to be 0. There might be small portion that is existing, but it will be approximately 0. It will have no effect on the surroundings. Okay, it will be 0. So that's what happens with the toroid and the solenoid. So if you take this case also, like how for a solenoid, the magnetic field is existing within the windings. Here also the magnetic field will exist only within the windings. And if you look at that, and for that, what we will do is, we will take an Amperian loop inside the toroid. And let me take the radius of that Amperian loop to be R. That is the average value. Right. What does Ampere's circular law state? The line integral of B vector dot dl vector is equal to mu naught into the charge enclosed by the Amperian loop. That is the statement. Right. So when I talk about this line integral here, we know that due to this coil, the magnetic field is going to be in which direction? First, let me take the current to be in such a way that the current is going into the plane at the top and coming out of the plane at the bottom. So when I take a curve, when I apply the right hand thumb rule, I can say that the magnetic field is in this direction. So this is the direction of magnetic field. And what I will do is I'll consider a small a small element here. It's not a current carrying element, correction. It is a small element on the Amperian loop, which is dl. That is this dl. So most of the cases, how will we do it? B and dl will have the same direction. See, dl is the thickness of it. Don't get confused that I drew an arrow mark, that is the direction of dl. No, dl is going to have the same direction as that of the magnetic field itself. So this can be the direction of dl also. If having said that, the line integral of B vector dot dl vector will be equal to how much? It will be B into dl into cos of 0, which is going to be 1, which will be equal to mu naught into this current enclosed is there, no? Let's say there are n number of turns that are present. Capital N is used for number of turns, small n is used for number of turns per unit length. So let's say this toroid has n number of turns associated. Then what is going to be the total current that is present in it? So can I write it as capital N into the current through each loop? So current through one loop, if I take it as I, current through n loops is going to be capital N into I, because that is going to be the effect that will get added. You should not look at them like that the coils are in series and the current is going to be the same. No, it is the effect. So if there is only one winding, it would have produced a value of this much value. If it would have produced an X value, if there are n number of times, it will produce a value, it will produce a net effect of n into X. That is why I wrote n into I. Right. So B is uniform, I can take it out. B into, what is the line integral of dl? If I add all the dls on the Amperian loop, what am I going to get? I'll get the circumference of a circle, and it is going to be 2 pi r is equal to mu naught into capital N into I. So I'll bring the 2 pi r to the right hand side. B will be equal to mu naught into capital N divided by 2 pi r into I. So the number of turns for a circle, 2 pi r is the length. So the number of turns per unit length is what is called as small n. So this is going to be equal to mu naught into N into I. So if you observe, solenoid and toroid are going to have the same magnitude of magnetic field. The only difference is for a solenoid, the value of small n is defined as capital N divided by the length, whereas for a toroid, it is defined as capital N divided by 2 pi r. So this is the value, and this is all about the toroid. Clear? Make a note. Those are online. Did you understand? You can find the link for videos whenever you can go to YouTube directly and have a look at it. Or you want me to share the link? Shall I put it? Okay. We'll wind up with this. If you have any other questions, you just let me know. If you have time, I'll teach, or else I'll record and give it. So yeah. So you have first five chapters, huh? Fifth full hour. Okay. Okay. Those are online. Any questions? Those are online. Any questions?
No, sir.
Okay, then we'll wind up. Okay.
Thank you, sir.